So the Gang of Four collected 23 object-oriented solutions to common programming problems, which they published as a catalog in design patterns, and they organized these patterns into three categories: behavioral, creational, and structural patterns. The book was an immediate success and permanently altered the software industry since it provided a catalog of patterns developers could incorporate into their own code and showed the benefits of identifying and using patterns for other design problems. The Gang of Four even invited the community to extend their catalog of patterns so that designers and implementers have a rich inventory of solutions to choose from, much like an IC catalog or catalogs for hardware supply, toys, etc. But a weakness with their book is the difficulty in differentiating some of the patterns from one another. To understand how the patterns within a category behave differently from each other, how they overlap with one another, which are orthogonal, which are mutually exclusive, and how patterns might be combined to solve specific system requirements. So to get a better understanding of the patterns, let's pick out the ones that work in a limited part of the solution space, which solve a problem at a particular scope, and arrange them from the largest portion of the solution space to the smallest in the catalog. For the complete solution space, the largest pattern in the catalog is interpreter, the execution system for programs. It fills the entire solution space because the code for the system is implemented entirely within the interpreter. Next, we identify the group of patterns that describe how certain objects work together. Their integration, how to get different objects to fit in the system. Next, the set of patterns which change an object's behavior while the system is running, depending on certain factors, conditions, etc. Then, the set of patterns which allow you to change the algorithm in use for a particular object. Examples include formatting of text or other output, or one sorting solution over another depending on their present sorting order, quantity, etc. And finally, patterns at an even smaller scale, where a set of objects share an algorithm, but you need to replace elements of the algorithm. So you only change certain sequences or data in the algorithm, but still retain the structure and behavior they all hold in common. So those are the Gang of Four patterns we could group together as scoping patterns. But looking at this collection, one could see they didn't cover the full scope that might exist in a solution, whereas our goal is to identify and catalog all the patterns that might be useful in a software system. The Design Patterns book didn't cover other ways to implement the system, nor does it list solutions that can be much bigger than just one machine or process. And in addition to patterns which partition the solution into different objects, we also need patterns which separate solutions down to the smallest pieces of executable code. Removing those scoping patterns, the next task was to identify solutions at the bottom row, how to find and run those executable sequences. In an object-oriented system, sending a message involves a receiver, a selector, and the arguments. Normally, code holds a direct reference to the receiver of the client's messages in a variable or a constant. But sometimes you don't have or don't want that object to be directly accessible by the client code. There's a pattern category to dissociate the receiver from direct access by the client. And there's another category to capture the entire message or parts for use or reuse in another sequence. From this perspective, we can see these patterns deal with object messaging. Message dispatching in particular. That is, how do we get the message to the right object so it runs the correct executable sequence? So let's build a table for patterns that deal with using message elements to perform an executable sequence. But that's a very narrow definition of messaging patterns. Let's create one for messaging patterns in general. This table is made up of solutions of any sort that deal with the handling of messages. The messaging paradigm, central to object-oriented programming, means we can bring any high-level messaging concept into play for a single message sent to an object. In fact, under the messaging perspective, an integration pattern is actually a form of message transformation. From this perspective, the adapter pattern transforms a message intended for one kind of object to a different message for another kind of object. And a facade transforms communication with a single object to communicating and operating a whole group of objects. And control statements, so fundamental to procedural and functional programming, aren't needed in object-oriented languages. They're handled with messages that route messages, control, if you will, to different sequences depending on the condition. Now the next set of patterns the Gang of Four cataloged are mainly the ones they called the creational patterns, but examining them closely and how they differ from one another, we find there are patterns that define object creators, patterns that define an object state, and finally, a pattern that sets a boundary on the population of class instances. Viewing them in this way, we see they relate to an object's life cycle. So we can expand the patterns in this category to all the ways we deal with the creation, lifespan, and destruction of objects. And finally, after reclassifying all the other patterns in the book, we're left with the iterator pattern. But I recommend you avoid iterator, because it doesn't actually conform to the object-oriented paradigm. It's a fallback to the procedural or functional programming model, treating the object as a data structure and pulling elements from it for processing. The message-oriented way to code an operation on a collection is to send a message to the collection to perform the executable sequence, or pass it as a closure, specifying how to process its elements.